Hello, welcome to Lecture 8 of the online course on Explainable Machine Learning and Artificial Intelligence. In Lectures 6 and 7, we discussed model-agnostic explanation methods that can be applied to any black box model. In this lecture and the next one, we will instead talk about methods that are specific to a particularly important class of black box models, neural networks. The global goals of this lecture and the next one will be to first contrast structured and unstructured data and highlight the importance of extracting useful features from unstructured data. This is something neural network models are particularly good at. We will next recall the basics of neural networks and deep learning, which we will need to discuss interpretability. In this lecture, we will then review two first methods for interpreting neural networks called feature visualization and network dissection. Then in the next lecture, we will define and review a second set of explanation methods for neural networks called attribution methods. And we will in particular focus on the key concept of saliency maps. Before we start, why do we want to focus specifically on neural networks? Obviously, neural networks are everyday nowadays, but why is this the case? To understand the fundamental reasons, we need to go back to the distinction between the two types of data that I mentioned when we defined the general framework in Lecture 3. Data used in machine learning comes in two fundamentally different types. The type we mostly discussed so far is structured or tabular data, which is organized in terms of engineered and interpretable features such as temperature or mortgage amount. It is important to realize that such data has been pre-processed to extract meaningful features. In contrast, a second type of data is unstructured data that corresponds to raw measurements such as pixel values in an image, sound waves, movies, text, and so on. For this kind of raw data, the values of the inputs are not directly interpretable. Moreover, it is in general not directly clear how to pre-process such data to extract features that would be at the same time relevant for the underlying prediction task and interpretable to human users. Neural network models are a class of models that excel at making predictions from unstructured, raw data such as images. They are based on two key properties. The first property is that neural networks take as input raw data and then learn to extract relevant features in their hidden layers, so that they do not require feature engineering to make predictions. One way to explain the output of neural networks is therefore to interpret the features that they extract in their hidden layers. A second key property of neural networks is that they are differentiable with respect to both their parameters and their inputs. From the point of view of interpretability, this property can be directly exploited to generate local explanations. In this lecture and the next one, we will go more into details on these 2 points and how they are used for developing explainable artificial intelligence. But first, let's start with a short reminder of the fundamentals of deep learning and neural networks. This will be just a very short recap of the essential properties that we will need when discussing explanation methods for neural networks. This is not a course on deep learning. It assumes that you have seen neural networks elsewhere. The central building block of neural networks are, of course, neurons. But what is a neuron within artificial intelligence and machine learning? It's a very simple function that takes a set of inputs y1 to yn and applies a series of 2 operations. The first operation is a linear combination. Each input yj is multiplied by a synaptic weight wj and then summed to produce a total input x. The second operation is to apply a nonlinear function to this sum, and typically this nonlinear function is a rectified linear function, also called the ReLU. So, in summary, the input-output function performed by a neuron is a composition of a linear operation and a pointwise nonlinearity. From the point of view of machine learning, a central property is that such a composition can be easily differentiated by using the chain rule. Indeed, using the chain rule, the derivative of the output y with respect to a quantity a, which is either an input or a synaptic weight, can be written as a product of the derivative of f with respect to its total input x and the derivative of x with respect to a. The first term, the derivative of f with respect to x, is simply the local slope or gain of the nonlinear function f. The second term, dx over dA, depends on what a is. If a is a synaptic weight wj, dx over dA is the input yj. If a is the input yi, dx over dA is instead the synaptic weight wi. So far, we looked at one individual neuron. Neural networks consist of sets of neurons organized in layers. A layer L is a set of neurons that take as inputs the outputs of the previous layer, L-1. Each neuron J in layer L multiplies the outputs of layer L-1 by its own set of weights, so that the synaptic weights between layer L-1 and L depend on two indices: the index of the postsynaptic neuron J and the index of the presynaptic neuron I. The set of weights between layers L-1 and L therefore defines a matrix which we will call W with a superscript L-1. Using a vectorial notation where a vector y superscript L consists of the activities of the neurons in layer L, the activity YL in layer L is obtained by first multiplying YL-1, the vector of activity in layer L-1, by the synaptic matrix WL-1, and then applying to each neuron the nonlinear function f. So, the transformation of activity from one layer to the next is given by a sequence of a linear operation and a pointwise nonlinearity. Finally, the full neural network is obtained by stacking a set of layers after each other so that the input-output transform performed by a neural network is a sequence or a composition of linear-nonlinear operations. This compositional linear-nonlinear structure of neural network models endows them with a key property: the ability to easily differentiate the activity of any neuron in one layer with respect to the activity in another layer. Let's illustrate this property for an example network consisting of 4 layers. Imagine we want to understand how much changing the activity of neuron I in layer L-1 changes the activity of neuron K in layer L+2. For this, we want to differentiate YKL+2 with respect to YJL-1. Because YKL+2 is related to YJL-1 through a sequence of operations through intermediate layers, this differential can be expressed using the chain rule. And the chain rule can in particular be applied with respect to the activity in layer L. Applying the chain rule with respect to layer L gives a sum, where each term is a product of the differential between the output activity YKL+2 and the activity of a neuron in layer L, and the differential between the activity of the same neuron in layer L and the input activity YI-L-1. This second term is simply the differential of the activity of neuron J in layer L with respect to its input I in layer L-1. Using the expression of the differential for individual neurons that we wrote a couple of slides back, the second term is simply the slope of the nonlinear function for the neuron J in layer L multiplied by synaptic weights. This shows that the differential of activity in layer L plus 1 with respect to the activity in layer L minus 1 can be expressed as the differential of the activity in layer L plus 2, but now with respect to the activity in layer L, multiplied by the gains at layer L and multiplied by the transpose of the synaptic matrix between layers L minus 1 and L. Applying the chain rule multiple times, the differential can be expressed as a sequence of multiplication by gain matrices and transposes of synaptic weights between layers. This sequence of matrix multiplications is what is called backpropagation, and it is essentially a form of automatic differentiation for neural network models. The essential point here is that backpropagation can be used to compute the differential between any two quantities in a neural network. The most classical use of backpropagation is to train networks. This corresponds to computing differentials of the loss function with respect to network parameters, the synaptic weights. But differentiation properties of neural networks can also be used to generate explanations. This can be done, for example, by differentiating the output of the network with respect to inputs, to understand how changing inputs changes the outputs. Another possibility is to differentiate the activity of specific neurons or layers with respect to inputs to understand which features they encode. In the rest of this lecture and the next one, we will talk about different types of explanation methods that use these different types of differentiation. But before moving to explanation methods, there is one additional general concept that I need to introduce, the concept of the architecture of a neural network. So far, I told you that a neural network consists of a series of layers of neurons. The structure of the sequence of layers and of the layers themselves defines what is called the architecture of a network. In particular, individual layers can have additional structure in their weights, and this defines different types of layers. One of the most common types of layers is the so-called convolutional layer, used in networks that process images. In a convolutional layer, the individual neurons are arranged on a three-dimensional grid. In this illustration, each neuron in a layer is shown as a small cube, and altogether the neurons form a larger cube. Two of the dimensions in this cube correspond to the x and y coordinates of the image. They define rows of neurons with spatial activations, meaning that neurons in one row correspond to a pixel in one part of the image. The key property of a convolutional layer is that the synaptic weights received by neurons in different rows are identical up to a translation along the spatial coordinates of the image. This property is called weight sharing because during training the weights of different rows are updated at the same time. So the weights are identical across rows, but for different neurons in a row. As a consequence, each slice of the cube corresponds to one set of spatial weights, translated across the image. Each slice therefore computes a convolution of the spatial inputs with respect to one spatial filter, and that filter is different for different slices. The different filters corresponding to different slices are called the channels of a convolutional layer. Another very standard type of layer is the pooling layer. A pooling layer takes as input a two-dimensional pattern of activity illustrated on the left and simply computes the maximal activity in different small patches, illustrated here in different colors. So a pooling effectively downsamples the activity in a spatial pattern of inputs. Putting together a sequence of convolutional and pooling layers leads to a convolutional network, one of the most widespread types of neural network architectures. This figure illustrates an example of a convolutional network, VGG16. It consists of a sequence of convolutional layers, shown in green, and pooling layers, shown in blue. The precise number of layers, their size and shape, define the precise architecture. The most common use of convolutional networks is to classify images by associating a label to each image. The most famous benchmark for this type of task is the so-called ImageNet dataset, which consists of a large number of images with associated labels. So, in response to an input image, the final output of a convolutional network are probabilities of different labels or classes. These probabilities are generated by taking the output of the final convolutional layer and using it as an input to a fully connected layer, a standard layer without any structure. The output of this fully connected layer is then fed into a final layer that simply applies a softmax to generate probabilities. So the final layers of a convolutional neural net are very similar to a neural network representation of the logistic regression, a representation of logistic regression that we covered in Lecture 5. Going back to the convolutional network, the outputs of the final convolutional layer play the role of learned input features to a fully connected layer that acts as a logistic regression and generates logits for different classes, which are then converted into class probabilities. This similarity of convolutional networks with logistic regression opens the door to using similar tools for generating explanations of the network's outputs. Let me summarize the main points of this brief recap on the fundamentals of neural networks. From the perspective of explainable and interpretable AI, the structure of neural networks suggests that we need to focus on hidden layers to understand the learned features, and the differentiability properties of neural networks open up the possibility of using gradients to understand how the features and outputs depend on inputs. We will next turn to specific approaches to explainability that use these methods. The first approach we will cover is called feature visualization. The goal of this approach is to understand what features the intermediate layers have learned by directly visualizing the preferred stimuli of different neurons. The preferred stimulus of a neuron is the input or set of inputs to the network that maximally activate a neuron. This is an approach directly inspired by neuroscience, and this is why we use the expression stimulus as a synonym for input. This approach was pioneered by a researcher named Chris Olah, and the examples I will be discussing here are based on his web publication on feature visualization, which can be found on this link. To describe feature visualization, we will focus on convolutional networks processing images, but this approach can be directly applied to other kinds of networks and other kinds of stimuli. The examples are based on a specific type of convolutional network called the GoogleNet, illustrated here, and which was trained on the ImageNet dataset. This network consists of a sequence of convolutional layers, and the goal of the feature visualization approach is to look for artificial input images that maximally activate neurons in different layers. So the goal is really to generate images that do not exist in the dataset, but correspond to features learned by neurons in the network. To give you a taste of the results, this is how these preferred images look like for neurons in different layers, from left to right, going from early to deep layers. What you can see is a clear increase in the level of abstraction in preferred features. Neurons in the early layers tend to respond maximally to low-level features such as stripes and edges. And as we go deeper in the network, neurons tend to like textures, then increasingly complex patterns, and eventually parts of objects or even objects themselves. These abstract artificial images give us a sense of what kind of features the neurons in different layers have learned. But how are these images generated? I haven't told you this so far, so let's go into the details. The core of this approach is based on optimizing inputs that activate specific neurons. This optimization is done by using the automatic differentiation properties of neural networks that I have described a couple of slides back. So concretely, we choose a unit, a neuron in a given layer, and choose a random initial image as the input. Then we compute the differential, the gradient of the activation of this unit with respect to the pixels in the input. Next, we update the input in the direction of the gradient so that the activation of the unit is increased. This gives us a new artificial image as the input. And these two steps are repeated until the input converges to an image which generates a local maximum for the activation of the neuron that we are considering. So this sequence of updates leads to a sequence of images which eventually generates a preferred input for the neuron we started with. This algorithm can be applied to any neuron in the network, but these neurons are organized in layers and channels. So ultimately, we have the choice of which activity we want to optimize. The most straightforward is to optimize the activity of a specific neuron. In convolutional layers, each neuron has access to one spatial piece, one patch of the image, so this will generate images within the patch corresponding to the neuron we are looking at. Because of the structure of a convolutional layer, all neurons within a given channel have a similar type of preferred input, but center in different patches of the image. So instead of optimizing the activity of a single neuron, we may want to optimize the activity of the full channel. The images that I showed you on previous slides were obtained precisely by optimizing channel activations. Each convolutional layer is formed of a set of channels, so we could optimize the activation of a full layer, but this generates images that are a little bit harder to interpret. Finally, remember that the last two layers in the network are not convolutional. They are similar to a logistic regression. They compute class logits and class probabilities, so maximizing the activity of neurons in these final layers will give us information on what stimuli features maximize the classification in different classes. Maximizing the activity of neurons in the final layers is directly related to attribution methods which generate explanations for specific inputs. We will talk about attribution methods and final layers in the next lecture. In this lecture, we'll focus on feature interpretation for the intermediate layers. An additional practical aspect is there are several options for optimizing the input image. One option is to search through the training data for images in the dataset that maximally activate a neuron or a channel. An alternative, which we already discussed, is to generate new images. The outcomes of the two approaches are illustrated here for a couple of example neurons. Comparing the results, a potential advantage of this second method is that it extracts more abstract features that are shared by different images in the dataset. For example, for the second neuron from the left, looking at examples from the training data, it is not clear whether the preferred input of this neuron are animal faces or snouts. The artificial image generated on the bottom answers this question to some extent. So we went through the basics of the algorithm for generating feature visualization. Let's next turn to some of the challenges for this approach. The first challenge is to generate diverse visualizations. I told you that the feature visualization generates local maxima for the activation of a neuron or a channel. But potentially there can be many such maxima, so it might be important to sample a variety of them. The second challenge is that this approach really focuses on individual neurons or channels. However, in general, the neurons in a neural network interact and are correlated, so the question is how to take these interactions into account. A third, a more technical challenge is that the direct gradient update that I described often leads to artifacts, so it's useful to have a regularization method that can take care of that. Let's start with the first challenge, diversity. Here, the central question is whether individual examples of preferred inputs show the full picture. As I mentioned earlier, the optimization approach used to generate preferred inputs converges to a local maximum, and therefore gives a single example of a preferred input. But typically there are many local maxima, and therefore many potential preferred stimuli. To sample them, one approach is to repeat the optimization multiple times by starting from different random input images, or even from different dataset examples as the initial point in the optimization. Another option is to add a diversity term to the objective function to penalize similarity across generated examples. These images show examples of this approach. The image on the left shows the output from one simple optimization. The images in the middle show a set of optima obtained using multiple initializations and a diversity term in the objective. Finally, the images on the right show examples from the dataset that maximally activate the neuron. The main message here is that all these images look quite different, so it is in practice not necessarily easy to identify a single preferred feature for a neuron. Most neurons will, in fact, prefer mixtures of different sets of features. The next challenge are interactions between neurons. Feature visualization looks for preferred stimuli of individual neurons, but an important question is whether single neurons are the right semantic units. To address this question, a useful approach is to adopt the perspective of a downstream neuron. This downstream neuron receives inputs from neurons in the previous layer, multiplies them by synaptic weights, and sums them. So the total input to a downstream neuron can be written as a scalar product between a vector of synaptic weights, W, and a vector of inputs, Y. This scalar product can be interpreted from a geometric perspective, as we did for linear regression, where the maths were identical. So the vector of synaptic weights can be interpreted as a specific direction in the input space, where every axis is one of the inputs, or equivalently, the activation of one neuron in the previous layer. Maximizing the input to this downstream neuron is then equivalent to maximizing the activation along the directions W in the activation space. This geometric interpretation can then be used to address the question we started from. Are single neurons the right semantic units, or do we need to take interactions into account? In this geometric picture, the activations of individual neurons correspond to the individual axes in the activation space, while different combinations of neurons correspond to vectors or directions in this space. Our question then becomes, are inputs along basis vectors more interpretable than inputs along other directions? To address this question, we can look for inputs that maximize the activation along different directions in activation space and try to interpret them. In his study, Chris Olah did this first by looking at random directions in activation space and optimizing inputs to maximize the activity along these random directions. This figure shows a couple of examples for random directions with different layers of the network shown in different columns. As before, the top shows examples from the dataset and the bottom artificially generated images. Instead of choosing random directions, another approach is to look at a pair of neurons and then look at directions in the activation space that interpolate between them. This figure shows optimal stimuli for different interpolations between the two neurons. Ultimately, it is difficult to directly conclude from these type of examples. One approach can be to look for maximally interpretable directions, but this is essentially an open question. The third and final challenge that I mentioned is the issue of artifacts in the image. Initially, I told you that the gradient can be computed with respect to the values of individual pixels in the input image, so that the values of different pixels can be individually updated. This approach often leads to high-frequency artifacts, illustrated in this figure, and this points to the importance of using a regularization when computing gradients and updating the input. Several types of regularizers can be used in principle, for instance, high-frequency penalization, robustness to transformations such as translation, rotation, or scaling, or even a learned prior such as generating images from a generative model. Chris Ola's webpage provides an interactive interface for testing the effects of some of these regularizers. In particular, it shows that using a simple combination of jitter, rotation, and scaling produces already good results. To summarize this part on feature visualization, this approach provides a highly intuitive way of visualizing the learned features of neurons or channels in a convolutional network. It is in particular clearly very visually satisfying and can be combined with other methods. However, an issue with this method is that it looks at individual units or channels one by one, and there are simply too many to look at. It is not immediately clear how to summarize the outputs of feature visualization. Another issue is that many obtained visualizations are ultimately difficult to actually interpret and explain. We will now turn to a second approach for interpreting features in neural network models called network dissection. Network dissection is an approach developed by David Bao and colleagues in a 2017 study called Network Dissection: Quantifying Interpretability of Deep Visual Representations. The goal of this approach is to test a specific hypothesis, which is that hidden units in a deep neural network learn disentangled concepts. What are disentangled concepts? These are, in a sense, fundamental properties of an object, such as, for example, its color and shape. Identifying algorithmically these fundamental properties is in general difficult. So the main idea of this approach is to directly label units in a trained network using human concepts, and then use this labeling to track the decision process in the network. Concretely, the approach consists of a series of steps. The first step is to get a dataset of images where individual pixels are labeled with human concepts. The second step is to measure the activations of different channels in a convolutional neural network in response to images from this dataset. And the third step is to quantify the alignment of measured activations with human-labeled concepts. To apply this approach, Bao and collaborators collected a specific image dataset labeled with human concepts. They called this dataset BROADEN, which stands for Broadly and Densely Labeled Dataset. This dataset plays a key role in the network dissection approach. So let me describe what it looks like. The dataset consists of images which were segmented to pixel level by human subjects, who then annotated different parts of the image with concepts at different levels of abstraction. For example, in some cases, the whole image was annotated as street or swirly, concepts that belong to the broader classes of scenes and textures. In other cases, parts of the image were annotated as flower or headboard, which are examples of objects and object parts. Patches of images were also annotated with more abstract concepts such as color or material. Concretely, every image in the dataset was associated with a set of concepts, which each corresponded to a set of pixels in the image. This is how the dataset was created. The next step was then to use this dataset to associate units in a network with different concepts. This was done using a procedure of unit scoring. In this procedure, different images from the dataset were given as inputs to a trained convolutional network that is being probed. The activation of different units in the convolutional layers was then measured. Remember that each unit in a convolutional layer corresponds to a patch in the original image, so to a set of pixels in the original image. This set of pixels can then be compared to different sets of pixels that correspond to different concept labels associated with the input image. Comparing these sets of pixels, for each unit we obtain a similarity score with each of the labels of the image. In a final step, for each unit, the highest score determines the label, meaning which concept it encodes. Many units detect the same concept. For example, there are 95 dock channels in the VGG network trained on ImageNet. This was a description of the general procedure. Let's now look at some examples of the outcome of this analysis. Each panel in this figure shows 3 images that led to the highest activation of one example unit in the network. The label on the top left of the panel corresponds to the label assigned by the scoring procedure for this unit. The label on the top right is an independent description assigned by a human subject to the same subset of images. This is used as a validation of the scoring procedure. For example, the unit on the top left was labeled as responding to color red, but by both the scoring procedure and the human subject. The one below was labeled as color, and the unit at the bottom was labeled as sky by the scoring procedure, but blue by human subjects, pointing to some possible issues with spurious correlations. This can of course be done for units in different layers of the network. From left to right, the different columns in this figure correspond to units from early to deep layers in the network. Altogether, we recover a finding from feature visualization. Units represent increasingly more abstract features as we go deeper across layers. Here, units in layers 2 and 3 appear to encode textures and materials, but increasingly encode objects and object parts as we go deeper in the layers. This was a concrete illustration of labels obtained for a couple of units in different layers. Going beyond individual cases, these labels can be used to obtain an overall quantification of the types of features that different layers represent. To obtain such a quantification, Bao and collaborators defined a quantity which they call the number of unique detectors. This is a number which summarizes for each layer the number of unique concepts aligned with units in the layer. This quantity can be computed separately for different classes of concepts and different layers. This figure summarizes how the number of unique detectors for different concept classes evolves across layers in an AlexNet convolutional network trained on the ImageNet dataset. What this figure shows is that the first layers represent mostly low-level features such as color and texture, shown here in green and light blue. The deeper layers instead represent increasingly high-level features, in particular objects, shown in dark blue, and parts, shown in red. This quantification in terms of the number of unique detectors therefore provides us with a simple tool to interpret which features are represented by units in a given network. We have just seen how this quantification can be used to compare different layers in a trained network. It can also be used to compare different networks. This figure shows an extensive comparison between different types of convolutional networks such as AlexNet, VGG, GoogleNet, or ResNets. Each of the networks was moreover trained on a different dataset, including ImageNet and different datasets for places. For each combination of network and training dataset, the y-axis shows the number of unique detectors, the summary quantity obtained from the network dissection procedure. Different colors correspond to different classes of concepts, as before: objects, parts of objects, scenes, materials, textures, and color. The main conclusion from this figure is that different networks can be classified according to their interpretability. In particular, deeper network architectures appear to allow for greater interpretability. The Places dataset also appears to lead to greater interpretability than the ImageNet dataset. The number of unique detectors obtained through network dissection can also be tracked across training for a single network. This figure shows that it increases through training, and particularly strongly for most high-level category of objects. This confirms that units in the network learn to represent high-level features during training. To summarize this part on network dissection, this method provides an interesting manner to interpret concepts encoded by individual units. Importantly, it allows to detect concepts beyond the classes on which the network was trained. The main disadvantage of this method is that it needs a specific pixel-labeled dataset to probe networks. So this is in general difficult to extend to types of tasks other than image classification. Another limitation of this method is that it interprets individual units, but it does not really tell us how the units contribute to the actual output of the network. And this limitation also holds for the previous method we discussed, feature visualization. To summarize this lecture, we started with a brief recap on unstructured data and neural network models. A key idea is that neural networks learn to encode relevant features in unstructured data. We therefore discussed two interpretation methods specifically developed for network models: feature visualization and network dissection. Both of these methods aim to uncover the features learned by hidden units in a network model. But these methods do not tell us how the activation of different units in a network model leads to the output of the model. Ultimately, our goal is to precisely provide explanations for outputs. So, in the next lecture, we will cover a different set of methods that directly aim to generate explanations for the output produced by a neural network model in response to a given input. Stay tuned and see you next time.